Today we're going to learn a way to keep track of all the different possible combinations of things when you have more than one event going on. Okay, we did a little bit of this back before the break. Today we're going to learn how to make what's called a probability table. Later we'll learn about probability trees as well. I personally like probability tables a lot more than probability trees, although probability trees do have their place. So, we're going to talk about a game called 10 O's. So, in this game, you have 10 O's that you want to have marked out. You can place all of your O's on one number, place them each on a different number, or do any combination of numbers that you want to do. Okay, I'm going to roll two 6-sided dice. I can't find my other one, so I'm going to roll one twice. And if you have an O above that number, you're going to cross out the O over the number that's called. The winner will be the first person to get all 10 of their O's crossed out. So, if you haven't done so already, place your 10 O's. Does anyone need some more time for that? I'm looking around and no one seems to be writing anything down currently. Does anyone need any more time to put their 10 O's? I see a couple people writing but not nodding. You guys have got to talk to me. Do you need a little more time? Okay, then just say so. It's not a big deal. All right, anybody not finished? All right. First number is 3. Second number is 5.
So was you cross out numbers that are above
You
the
cross out just one O that's on the 3. Right? So if you have 3 on the 3, you don't get to cross all of them off, just one of them. Oh, does that change it for some of you? We're not too far in. Does anyone want to change how they arrange things? Okay, I'll give you a minute to change how you arrange things. And then we'll start over. You don't get to go, oh, he's already called a 3 and a 5. We'll start over for everybody. We'll start over. Pardon? So you need 10 O's on your paper, please, that have not been crossed off. All right. Are you ready? Is anyone not ready? Let me ask it that way. Okay. I'll wait another minute or so. All right. Let's try this again. First number is 5. Next number is 9. Next number is 3. Shh. Next number is 6. Next number is 11. Next number is also 11. Next number is 7. Next number is 8. All right. Shh. Next number is 7. Next number is 8. Next number is 8.
Yo, I just stacked them on 8.
Don't say 8 again.
Don't say 8 again.
Next number is 7.
I just stacked them with this.
No 7s and no 8s.
Next number is 12.
Yes.
I need 2 more.
Next number is 6.
I need 3 more. I need 4 right now.
Next number is 10.
One more. 2 more.
All right. Shh. Next number is 4.
I'm done. I did it.
All right. Shh. All right. So, tell me how you had yours arranged so that I can double check to make sure you haven't cheated here. Go.
I just did 1 on 3, 4, 5, 6, 7, 8, 9, 10, 11.
Okay. So he did it this way.
Hold on. What did he say? I went back to my original.
Oh, yeah.
And it did. We did do one of each of those. Okay. What number do you think got called the most? 7 and 8 both got called 3 times. 6 got called twice. 11 got called twice, which is kind of weird. And the rest of them only got called once, which is also a little strange.
I needed another 3 and a 10.
Another 3 and a 10?
I just needed 2 also.
I need 1, 2,
No one with my strategy. I didn't know.
All right. So, let's take a look at this. Gerald's strategy for the 10 O's game was to place an O on each number from 1 to 10. He was frustrated that his strategy of placing his 10 O's was not working, so he decided to analyze the game. Inspired by multiplication tables, he decided to make sense of the problem by organizing the possibilities into a probability table like the one shown at the right. So what we have is one dice 1 through 6, or one die 1 through 6, the other die 1 through 6, and you're going to add those two together. So let's fill in the table. This will be 2, 3, 4, 5, 6, and 7. And this will be 3 going up by 1. And then 4 going up by 1. So how many total combinations do we have here? 36 total combinations. So if we look at the 10 O's board, what was the first thing? 1? What's the probability of getting 1? 0. Since he chose 1 to 10, he was never, ever, ever, ever going to win, was he? Had no hope. Probability of getting a 2 is what?
1.
Out of 36. Not particularly good. So for those of you who are waiting for a 2, wow, it's a little harsh. Probability of getting a 3 is what? How many 3s are there? 2 out of the 36. which is 1 out of 18. Probability of getting a 4, there's 3 of those. That's 1/12. Probability of getting a 5. How many 5s are there? There's 4 out of 36. That's a 1 out of 9 chance. Probability of getting a 6. 5 out of 36, which doesn't reduce, but it's a better chance than getting a 5 or any of the other previous ones. What's the probability of getting a 7? 6 what? 6 over 36. 1 out of 6 chance. That's actually your best chance, because when we get to 8, what happens? Starts going back down. It's 5 out of 36. Probability of getting a 9 is 4 out of 36, which is 1/9. Probability of getting a 10 is 3 out of 36, which is 1/12. Probability of getting an 11 is only 2 out of 36, which is 1/18. It's actually sort of surprising that we got a 12 that quickly. That's 1 out of 36. We only rolled the dice about, I don't know, 14, 15 times.
Who had a circle one, bro?
Okay, let's not out anybody.
We had it at the beginning.
My notes were the 2.
I thought we were only doing one dice.
Is that what you're doing, 1 die?
Yeah, because I heard you say that you didn't have 2 dice.
Oh, I said I'm gonna have to do it twice.
Yeah, I know that now.
Okay.
Because Sophia very earnestly told me.
All right. So here we have the theoretical probabilities for each of those. So you should probably, if you're going to play the game over and over again, not just once, when you're doing it just once, just don't pick one, right? But if you're doing it over and over again and you're going to keep your O's in the same places, where do you want the most O's to go?
7.
Yeah, 7.
Put them all on 7. You'll win eventually.
Yeah, how likely is that?
Eventually.
Eventually, you'll win
You just have to
once.
sit there for a while.
Yeah, after, a whole lot of times.
Just go from 5. Just go from 5 to 9. Like.
Yeah, maybe from 5 to 9, and put, more in the middle than on the edges. All right, so let's do the same thing for the rock, paper, scissors game. Let's make a probability and use it to find the probability of players A winning and the probability of players B winning, and is it a fair game? So what we'll do is for each person they can choose rock, paper, or scissors. And for this one, what we'll do, we're not adding these together like we were on the previous one. And you may have noticed that on this one, they're telling you this is what we're doing, right? For this one, I'm going to call this one player A. And the one going down, player B. So if player A chooses rock, player B also chooses rock, what's the result? It's a tie. Player A chooses paper, B chooses rock, who wins? A wins, right? Player A chooses scissors, player B chooses rock. Who wins? Player B. Player A chooses rock, player B chooses paper. That's a win for A. Oh, did I do it backwards? Sorry. Thank you. If they both choose paper, that's a tie. Player A chooses scissors and player B chooses paper. That's a win for A. And then here, player A chooses rock. Player B chooses scissors. That's a win for rock. Player A chooses paper. B chooses scissors. That's a win for B, and a tie here. So how do we figure the probability that A wins? But how do you figure it? Not what is it, but how do you figure that? It's 3 out of 9. There are 9 total possibilities. 3 of them have A winning. That's 1 to 3. The probability that B wins, there's 1, 2, 3 places where B wins. That's also 1 to 3. Is this a fair game? Yes. Because each one has the same probability of winning. Do the probabilities for player A winning and player B winning add up to 1? No. Why not? Because there's a third possibility. A tie. All right, let's look at another one. Let's imagine that you have a bag with a red block, a blue block, a green block, and a yellow block inside. You make 2 draws from the bag, replacing the block after each draw. So the first question is, are these 2 events, the 2 draws of a block, independent or dependent? Are they independent or dependent? Pardon? Independent, yes. Does it matter if you replace the block each time? Yes. Why? Because if we don't replace a block, there are fewer of that color, and fewer total blocks. What we have done is we have altered the sample space. If you alter the sample space, then the probabilities change. All right, so let's make a probability table. So what was it? Red, blue, green, and yellow? And I'll say that's draw 1 and this is draw 2. Now here there's not a winner and a loser like there was in the rock, paper, scissors game. You just have different outcomes. So here, and I'm always going to put draw one first, because sometimes we'll say, you know, it makes a difference. On this one it's not, because it says find the probability of getting a red block and a blue block. Either color can come first. So this is red, red. This is blue, red, green, red, yellow, red. This is red, blue, 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 green, blue, yellow, blue, red, green, blue, green, 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 yellow, green, and red, yellow, blue, yellow, green, yellow, and yellow, yellow. So how many total do we have? There's 16. So the probability of getting red, blue, or blue, red, because they said the order doesn't matter. Let's see, red, blue, blue, red. There's just 2 of those, right? It's 2 out of 16. It's a 1 out of 8 probability. So a table like this, and I know these are simple enough to where many of you could probably just do this in your head. Right, you could figure out, well, what are the different ways I could make red and blue? How many different probabilities are there? But especially if it's something complicated, God bless you. If it's something complicated, sometimes these are really helpful. Okay, your assignment is in the book.